Okay, hey. So can you see the screen with the paper on?
Not yet.
Let me check.
Now we just see like the browser page with us on it.
Okay. What about now?
Same. We're just seeing the Google Meets.
Okay. Interesting. Maybe I can.
But you could, if you could, it's the next tab, right?
Yeah.
Okay.
So maybe I can share my entire screen. Oh, it's the window I was sharing. That makes sense. Okay.
We can see it now.
Okay, great. Cool. Hello, everyone. Thanks for coming. Yeah, it's January the 18th, 2024, and it's 1 degree outside. So join me as I sip my hot chocolate and we can discuss the paper, Photorealistic Text-to-Image Diffusion Models with Deep Language Understanding. Photorealistic means that the images can have been taken by a camera in the world. And text means text captions, generating an image. How is that image generated? It's by a diffusion model. And the text is encoded via deep language understanding. That's the key insight into this paper. It uses large language models as opposed to classifiers for the text embeddings. So let's see what that looks like to get a visual, a picture of what we're talking about, first of all. So here I've got a text prompt, and that's the input. Okay, so a golden retriever dog wearing a blue checkered beret and a red dotted turtleneck. And so the first component is a frozen text encoder. That's just part of a large language model, because large language models with transformers have an encoder and a decoder. So it's the decoder, the encoder that we're using, which encodes the text, which is put into tokens, and then the tokens are put into word embeddings combined with positional embeddings and fed through this kind of self-attention transformer architecture to produce this embedding, which is semantically meaningful. Okay, so then the first step of the model is to go from this text encoder embedding to a low resolution image via a diffusion model, which is conditioned or guided by the text embedding itself. So you can see here that you have indeed a dog, and it's got a beret and it's blue, and the dog is wearing a red dotted turtleneck. That's incredible, I think. I think it's a testament to natural language itself, that natural language contains so much information to condition on. And when diffusion models are trained, conditioned on their inputs, that we're able to so kind of precisely describe natural scenes. And I think it'll be interesting to see what further developments are going to be made when the generated data in hand can take on other modalities and quantities of interest, when combined with the power of description using natural language and the understanding of that description via large language models. The second part of the model is a super resolution model that employs something called noise conditional data augmentation that would allow correction of artifacts in the model. I can spot at least one artifact in this low resolution image, and that's this saturation orange color. It looks slightly too saturated to be photorealistic, but with this noise conditional data augmentation, which is the method that's used to train the super resolution diffusion model, then this can get corrected for in high resolution images. And I think another interesting aspect is that if you were to increase this kind of noise augmentation, which amounts to adding noise to this, more noise to the lower resolution image, and then you were to change the text embedding to a different prompt, say you wanted a blue turtleneck instead of a red one, then you could use this base image to change that into a different image. And so it allows quite fine control using text of a super resolution image. So this is a paper by 14 authors, and the equal contributors are Chitwan Saharia, William Chan, and Mohammed Narazi. And a core contributor, amongst others, is Jonathan Ho, who is also the first author for at least 2 papers that this paper relies on in terms of the algorithms used. So one of those algorithms was cascaded diffusion models for high fidelity image generation. So that second part of the model, which is the upscaling super resolution. And that's the part of the model that employs the noise conditional data augmentation. And secondly, the classifier-free diffusion guidance, which is a method of guiding diffusion models via text without using the logics, the probability outputs of a classifier, but instead training a diffusion model jointly with embeddings and images in order to guide the diffusion model, and it's a way of trading off or increasing the alignment and getting better alignment for higher fidelity or higher quality image samples. So a number of developments have led to this paper, and it's a synthesis of different parts of AI research, including large language models as well. So this paper was published on the 31st of October 22 in NeurIPS, and its first version was in May 22, and it's got a similar title to this other paper, whose last revised version was in March 22. So this is an earlier paper, and it's got a very similar title: Photorealistic image generation via diffusion models guided by text. It's the same thing. So what's the difference? The difference is that this paper uses embeddings from a classifier of images into captions that was trained with joint samples of images and captions, and so that uses embeddings from a classifier, whereas this paper uses embeddings from a large language model that wasn't trained jointly with images and captions. The large language model was just trained using a large corpus of text. So their key insight or discovery is that the generic large language models, so sequences of embeddings from large language models that are frozen, so the embeddings are frozen, not trained in this diffusion paper, used as conditional input for classifier-free guided diffusion models, where the large language model they use is this T5 large language model, pre-trained on text only corpora, so the large language model is only trained on text, are surprisingly effective at encoding text for image synthesis. And they find that increasing the size of the language model in this combination of diffusion and large language model boosts both sample quality and text alignment to the captions. Captions match images much more than increasing the size of the text to image diffusion model. So it seems to be more important. It's the limiting factor is the size of the language model, the understanding of the text. Imogen, which is the model for this paper, achieves a new state-of-the-art FID score on a COCO dataset for 0 shot. So that means without ever training on this image text caption paired dataset, and just supplying from a validation set the text captions from COCO, generating an image. That image in distribution is more similar to the COCO dataset than other models, images produced by other models. That's a bit confusing to me because without ever training on the images in the COCO dataset, how can these images be similar in distribution to those images in the COCO dataset? But it's just better than other models. And human raters find these samples from the image, the text captions, to be on par with the human labeled COCO dataset itself in image text alignment. And furthermore, they assess in greater depth the image text alignment and sample fidelity using human rating on a new benchmark that they've developed of 200 prompts, which is 200 captions that generate samples of images that are then compared versus the samples of other generative models that take in captions as inputs. And the human rater is asked to decide what samples they prefer, from which model they prefer the samples. Okay, so let's go into the paper, looking a bit further into what this large language model is. It's a T5 encoder, and they explore different sizes, the largest of which is denoted this T5XXL one. And it encodes sequences of embeddings from token inputs. And then it maps input text into a sequence of embeddings. And looking at that paper, which is this one here, this is done in a number of steps, from tokenization, which is a fixed lookup table, then to word embeddings, then adding positional embeddings, although the positional embedding is done slightly different in this paper, and an encoder consisting of a stack of blocks consisting of self-attention layers and small feed-forward networks. And finally, layer normalization, where activations are scaled by their norm. And that means that the gradients are smoother, and it allows for stability of training and faster convergence. Also skip connections and dropout. So I'm not sure how these, if you ablate these, they would affect the model, but dropout perhaps makes it robust to noise or uninformative text or images. So here you see some examples. The natural scenes described are quite detailed in terms of the captions, and all of the details are captured by the image output. So I looked at this other paper, Glide, and Imogen outperforms this prior work. And what's the difference between the prior work and this work? Well, Glide uses a classifier for the embeddings, whereas Imogen uses a large language model that wasn't trained jointly on images and data and text data. And they both control for the type of classifier guidance used. So we can look at what that means. What is classifier guidance? The key contributions of the paper listed, I think it's quite, we can just list the contributions so we don't miss anything. So discovered that a large frozen language model trained only on text data are surprisingly very effective text encoders for text to image generation, and that scaling the size of a frozen text encoder improves sample quality significantly more than the scaling size of the diffusion model. There is a heuristic introduced called dynamic thresholding, which is about a sampling procedure in the diffusion model, and it's about the numerical stability of the intermediate steps of this diffusion model. In a diffusion model, you're going from a pure noise and denoising it step by step. And what researchers find when they try and guide these generative models via this classifier-free guidance, if you try to increase the guidance so that you achieve more alignment, then the fidelity tends to decrease, and there's a trade-off there. And one of the reasons that might be is because the sampling procedure becomes unstable when the gradient that is used for guidance becomes too large. So there's numerical error in sampling, and what that results in when you look at the image is that they become saturated. And why do they become saturated? because saturated pixels have a large amplitude. They have values close to 1 or -1, so black or white. And previously, methods that try to reduce this threshold or clamp the images at each step of generation, such that the pixel values fall between -1 and 1. And so the sampling procedure never has the opportunity to diverge. And in doing so, presumably introduces some error. And the way that they increase that error, which results in lower aligned samples to the caption, is introducing some, it's a smarter way of scaling the images. Instead of clamping them to -1 and +1 in pixel space, they're going to do this dynamically, which is taking a percentile of each image in the batch of the pixel values, and say it's like the 95th percentile, so the 95th out of 100 highest value pixel, and it could be less than 1 or more than 1. This point we might go down to the algorithm used to try and explain this. So this percentile right here, which is, say, p, it's a float, was 0.95, so like the 95th percentile in pixel space value of this, the pixels in this image. It could be more than 1 or less than 1. If it's less than 1, then this threshold value is set to 1, and the image does not get scaled at all. So if the image is within the bounds of the state expected by the diffusion model, it doesn't get clipped at all. But if it is more than 1, then S is more than 1.0. So all of the pixels in the image get scaled by S, not just those pixels that are more than 1 in amplitude. So it's going to scale all of the pixels in the image and bring them closer to a stable region of pixel space. And what the result is that you don't end up with kind of saturated images. So let's see if we can find an example of that.
And I have a question.
Yeah.
So how do I put this? This thresholding that they're doing, is it something that happens at like multiple steps within the model?
Yeah, it happens at every step.
Okay.
Of generation.
Okay.
Yeah. So yeah.
And one thing that I was wondering is that they're saying to avoid saturation, but does that mean that like once a pixel gets saturated in generation, it stays saturated?
Yeah, I'm not sure about that, but one thing is that if it's a natural image, then it's likely not going to be saturated, because there should be some bias in the data set that means that whilst it's possible with a camera, right, to take saturated images if your exposure is too large or too small, none of these over or underexposed images are in the data set because the data set has been curated. So that would mean that in training, there is few saturated images. And so that if you did enter a region of pixel space where the pixels are saturated, it means there's a inference time, training time, so a test train mismatch. So the scores in this sampling step could be inaccurate, and they might not be able to correct for that saturation. And so maybe that means that once they become saturated, it is very hard for them to become unsaturated, because the diffusion model doesn't know where to point in which direction to make them unsaturated.
Okay, that's it. Thanks.
So it happens at every step. So in a diffusion model, when you're sampling, you have a range of T steps, and this is usually a large number of steps, because these scores are not very smooth, and they're, what we say, is quite ill-conditioned. If you take a point in pixel space and find its score, and then find the Jacobian of that score, that's a matrix, and that matrix will have a large condition number, which means the ratio between its largest eigenvalue and smallest eigenvalue is large. What that means is that the score magnitude is large in one direction and small in the other direction. And so what that means is that you need to take a lot of steps so that you're faithfully following the curves of this score as you go through pixel space, if that makes sense. So T has to be large, and that's one of the reasons why diffusion models are slow, because you have to evaluate this score network 1,000 times, say if T is 1,000. And so, yeah, so this dynamic thresholding procedure happens at every step. And then after that dynamic thresholding, the sampling step, which is going to slightly denoise the image at each step. So take a little bit of the noise out. At each point, as well as conditioning on the image, you're also on the previous image in the sample step in this for loop, you're also conditioning on the text embedding, and doing that in a way such that the image is guided towards a high probability of the image being described by the text, and also a high probability of being a natural image. And it would be a high probability of being a natural image because these diffusion models are trained in order to minimize FID scores, which is a score for fidelity or image quality. So the effect overall of that dynamic thresholding is clear when you look at the images. So these are saturated. It uses static thresholding, the clamping of the pixels at each step of the sampling procedure. This one uses the dynamic thresholding, which scales all of the pixels if any one of the pixels has a value above 1 in magnitude. And so that allows all of the pixels to stay in an area in which they can be guided towards high fidelity images more faithfully. So then they highlight several important diffusion architecture design choices and propose efficient UNets, a new architecture variant which is simpler, converges faster, and more memory efficient. They've done a study which looks at the training time of this more efficient architecture compared to the training time of an originally proposed UNet, which is the UNet is the score network for the diffusion model. And in particular, we're talking about, I think, the UNet, which goes from the text caption to the low resolution image. And so here is the training time in days, and the efficient UNet is the difference between 2 days and 4 days. Another aspect of this paper is that the amount of data used and the amount of compute is colossal. So this is a Google paper. They're using TPU pods, and these consist of an extremely expensive compute, basically, training for a long time, and that allows them to use like on the order of billions of image text caption pairs in training this data. So that makes it extremely hard to reproduce this, and as well as that, because of ethical considerations, not even the code that was used to train this model has been released. And that's in comparison to this paper, which I believe has a repository, glides text to image, and so you can have a look at some. It might be the actual code that we used to train, or at least the pseudocode that was used to train this model. So that's one aspect. Let's look here. So they achieve a new state of the art of COCO. So that's the data set of image to text pairs of this, and that's zero shot. So it wasn't trained on COCO images, but it evaluated on them. And so these images that it produces are similar in distribution to those in this validation set. And then they used a human rating to find the image and this model to be on par with the reference images in terms of the alignment to the caption. So they do this by asking a simple question: which model aligns the text? Which model produces images that align to the text? Which model do you prefer? And the answers are yes, no, or indifferent. And so they find the imaging to be on par with the reference images themselves. So those images in the validation set. So these images are looking to these human raters to be on par with the actual images in the data set that was used for validation. And finally, they introduced this new.
Do we have image to text models? Like, because this is a text to image model, but are there a lot of image to text models as well?
I have no idea.
Okay, I was wondering if you could get like an image to text model and say which one do you prefer, and use that instead of a human.
Yeah. So the question would be like which pair of image and text are more closely related, and then it would give you one from an image to text model and a text to image model. That's an interesting question. I guess it would depend on how much like information relatively there is in an image in producing a piece of text versus a text which is used to produce an image. And the kind of the phrase an image speaks 1,000 words comes to mind. So maybe if it was an image to text model, then you'd have like a higher human rating. But I'm not aware of any image to text models that exist. What kind of architecture would be involved in going from an image to a text?
Neither. Well, actually, I did see one called Flamingo from DeepMind, and it was like a combination of whatever state-of-the-art encoding model exists or embedding model for images in a transformer architecture.
Okay, so in terms of changing the word embeddings to pixel values in a transformer architecture.
It would be changing the image embeddings into incorporating image embeddings into the sequence of text in a transformer, and the transformer was used to generate text.
Maybe it would be at the level of the decoder, because the decoder is the part which produces the text. But yeah, I think the pixel values would be encoded, so it would be like an image to semantic embedding encoder followed by a typical large language model decoder. So I guess it depends if this space of embeddings was semantically meaningful in terms of text.
Yeah.
Well, it should be, right? Because Clip was trained like that, for example. DALL-E 2, I think, uses Clip also. So those are the embeddings that were trained with matching image with text. So you can use the same embedding the other way around. Maybe there is not much interest to publish papers. Maybe we just haven't seen those, but you should be able to do that.
Okay, so we can now go through the components, the algorithms that are used to train this model in detail. The first one, the large language models, so pre-trained text encoders. Talk about two different types of models. So text encoders trained on paired image text data jointly are standard in text-to-image models before this paper, and they can be trained using a pre-trained on image text data. For example, this CLIP model, which was the model used in the OpenAI Glide towards photorealistic paper. And the image-to-text training objectives suggest that these encoders encode visually semantic and meaningful representations. Okay, so what we were just talking about, relevant for text-to-image generation task, and wonder if it would go the other way around. Large language models can be, so that's one model, the jointly trained image text data models. The second one they're comparing against are large language models that can be another source of these embeddings for use in text-to-image generation. And what do they say about large language models? So what claims can we make about them? They've led to leaps in textual understanding and generative capabilities. I think it's fair to say language models are trained on text corpuses significantly larger because there is more marginal text data than joint text image data available. I mean, the amount of text on the internet is terabytes per day or terabytes per hour magnitude. And so this T5 model is trained on this corpus, colossal cleaned crawled corpus, which contains a proportion of Wikipedia article. Is a proportion of this data set is Wikipedia articles, for example.
To me, one thing that this suggests is that, and no, this is a hypothesis. Maybe this is true. Is that basically like these embeddings are supposed to encode semantic concepts, and that basically the embedding space when you're training only on text and only on images is possibly the same, because the fact that you can just use this text as is from these, like from a frozen large language model, means that when you're interpreting it from the image space, it has semantic meaning incorporated into it, which I think is pretty interesting. Like, what if there's a vector space for semantic concepts that's shared between all different modalities?
I suppose it's kind of curious how that would be accessed. Like if it's just trained, the large language model is just trained on text. And so I see what you mean, that if there is one semantically meaningful space, then an image text classifier achieves the same semantic meaning as large language models. But empirically, they're showing that the guided samples using large language models have higher alignment to the captions than the image text models. And they're explaining this by saying there's just more data and the models are better. But what if you were to control for that? What if there was the same amount of image text per data as there was text data alone? And would they then have the same performance? And then if you were to take each component of that text to image, so take the image component away, you're just left with the text, and we have to train an embedding space on that same amount of text and compare that to an embedding space trained on simply images. Well, training simply on images wouldn't work because you need to condition on the text somehow. So the question, I guess, is like, yeah, it's this comparison here, text to image versus just text embedding space, trained with the same amount of text data, which performs better. And if they perform the same, then maybe there's the same amount of information available.
I guess what your hypothesis would imply, Peter, is that there is some inherent relationship between different concepts, both in language and in image. which would mean that maybe it's the relative difference in the distance in the vector space that defines what a concept is. So they're not absolute, but they're relative. I don't know.
Yeah, maybe something along those lines.
Mhm.
I also was thinking to myself, Clip was developed around the same time as T5. So the people who developed Clip, why did it seems like using a frozen large language model is simpler. But now the contribution here is just use the LLM. I guess this is kind of like a hindsight's 2020 thing, and it just when they developed Clip, it was like, this works really well, so we should publish it. And then now we're finding like, well, actually, we could have just used the state-of-the-art large languages models at the time to embed text.
One of the explanations is one of the ways that guidance was done was with classifier guidance, and for that you needed a classifier, which is here, and so you need something like Clip in order to do this. But when you go to classifier-free guidance, you're just relying on training the diffusion model jointly on the C, which is the text embeddings, which you no longer need a classifier, which is why it's classifier-free. So since this was later on in development than classifier guidance, I would suppose that's why Clip was used for this term first. And then once this paper showed that classifier-free guidance was able to achieve empirically better results, then they made the realization that you don't need a classifier at all, you just need embeddings that match the images.
Got it.
Yeah, so they explore classifier and classifier-free guidance or encoded embeddings from Clip and T5. Okay, another component of this paper are diffusion models. Diffusion models denoise in a number of steps by learning a score, which is predicting the incremental noise added to an image using an objective of this form, but this is a conditional model. So we've not only got a noise image, so it's not unconditional generation, but conditioning on some text embeddings in this case. And then once that score is trained using this objective, using that to point towards the denoise sample. And classifier guidance is a technique to improve sample quality whilst reducing diversity. What does that mean? So improving sample quality means images more photorealistic in terms of FID score typically, while reducing diversity means the images, say, of that dog, the retriever, was wearing a beret, and it had a blue beret on, and diversity would mean something like if the blue beret had a tartan pattern, as we saw, or a checkered blue and white kind of chef pattern, and reducing the diversity would reduce the kind of number of different types of berets that the retriever was wearing, for example. And that's done in order to increase the alignment. So by increasing the probability of the image being described by the text caption, by upweighting this W term, you can achieve better alignment because it weights against the probability of the image being high quality and the probability of it aligning towards the text. So setting W to 1 here disables classifier-free guidance. So from that, we know that classifier-free guidance is this term. So this is unconditional generation. So if we're disabling this term, we're disabling classifier free guidance. So we're just sampling from a probability distribution of images conditioned on the embedding. But increasing W strengthens the effect of the guidance because this term is upweighted and this term is downweighted. And so ImageN depends critically on this classifier free guidance for effective text conditioning. So to go into more detail, because it's not entirely clear from that description why you want to do this, we can look at this paper by Ho, Classifier Free Diffusion Guidance. And it goes into detail of classifier guidance, which was an earlier attempt, and classifier free guidance. So what's this? So this is your diffusion model conditioned on the embedding, and in this paper they worked out that modifying this to include a gradient of a classifier term has the effect of upweighting the probability of data for which the classifier assigns a high likelihood to the correct label, which rewards generative models in image alignment. And so by setting this parameter greater than 0, so turning this effect on, they can improve image alignment of the diffusion model, and at the expense of decreased diversity. So the temperature of the distribution is decreased, and whilst you get like less different looking samples, those samples are in a higher probability space in terms of the likelihood assigned by the classifier, and so that they match with the data C better. And whilst it's not necessary to apply them to a class conditional model such as this, with a model trained jointly on the embedding data and the images, so you could just replace this with epsilon theta of Z alone. They find that applying guidance to an unconditional model like that, which is just this, without the embedding, performs less well. So the effect of class conditioning and guidance seem complementary. So what I think that would point towards is that using an unconditional model and then putting this information into the sample via classifier is not good enough, because that classifier might not be a very good classifier. And to me, it's possibly unclear why that is. Maybe the classifier is not very good because it's very hard to train a perfect classifier, so that you would want to use a class conditional diffusion model as well. But it's then not clear why using a class conditional model alone is worse than using this extra guidance term. And I think the idea is that you're trading off samples which are high fidelity, which would be produced by this model, and terms that fit the data very well, at the expense of lower variance in the samples, lower diversity in the number of samples. But empirically, they've been able to perform better by, instead of training a separate classifier model, which is expensive in itself, choose to train an unconditional denoising diffusion model together with a conditional model parameterized by the embeddings, and using a single network to parameterize both models. And how do you train when you don't have the joint data? Well, you set the embedding to a null embedding. And so this term is just the class conditional model with the embedding set to 0. And this is the same network, but with the embedding set to the value of the embedding. And then they weight a linear combination of these. So I think discussion on why this works well is quite complicated. But they're saying that this model is inspired, the functional form of this is inspired by what looks like Bayes' rule, but a reweighting of Bayes' rule such that you can upweight this term here, which brings you closer to samples which would have been assigned high probability by the classifier, so samples that have high alignment. And it's more general in the sense that there's no longer a restriction on this term that it has to be a gradient of this scalar potential, because these score networks are unconstrained. So no longer do you need to train a perfect classifier, but you can trade off a joint model that is unconstrained with an unconditional model that is unconstrained, and optimize for those parameters that you're interested in, whether it's fidelity or sample quality or alignment. So these are like very empirical arguments. Yeah, so this would make sense for going from text to images, because I think it's really difficult to train a classifier that goes from images to text.
Then there's a question, which is, would classifier free lead to less bias as there's no judge in quotation marks, or is the benefit only to increase in compute efficiency?
No, the benefit is not only to increase compute efficiency, but I think the benefit comes from being able to trade off more easily in optimizing the metric that you're interested in. If it's alignment, then you can optimize alignment whilst not trading off fidelity. And so I think the idea is that for classifier free guidance, for any chosen alignment, the sample quality is better than this classifier guidance. In terms of bias, I don't think you can comment on that, because it's not clear, since these terms are all approximated. This isn't an actual generative model of photorealistic images. You know that because it produces images, for example, such as a snake that is made out of corn in this example here. So that's not photorealistic. So it's slightly different to how images are actually created in the real world. So because there's this kind of model discrepancy between actually generating an image in the real world and these models, and there's a discrepancy between classifying these images with text and the actual text that someone, maybe I, would write to describe an image. There's this difference, and we don't know how that can be accounted for. So sometimes the best we can do is to find a scheme that allows us to trade off for parameters of interest that we're interested in. And in this case, it's for a given amount of text alignment, we want to push that to the limit. We want to have as much text alignment as possible without decreasing the sample quality. And ideally, we'd have no problem in doing that. But because maybe we don't understand this technology as well as we might do in the future, there seems to be a trade-off that we're having to deal with using this method. Beyond that, I'm not sure I understand fully what's going on. So it would be interesting to see how this gets explained and described in future works. Okay.
And I'm just cognizant of time. We have about 10 minutes left, so you know.
Sure. Okay. So what have we not talked about? The robust cascaded diffusion models. Making the super resolution models aware of the amount of noise added via noise level conditioning significantly improves the sample quality and helps improving the robustness of the super resolution models to handle artifacts generated by lower resolution models. And that is done by, for this low resolution images, adding a small amount of noise and training a upscaling super resolution diffusion model conditioned on the amount of noise that was added to augment this input image. And when this super resolution model is aware of that, is able to correct for artifacts by assigning the artifacts to the noise that was added in the data augmentation. And so it's a way of correcting for artifacts such as saturation in the original image and changing the image based on adjustments to the prompt. They found that was critical. So they use this kind of augmentation level, which is the noise added to the smaller dimensional image between 0 and 1, and found small values close to 0 to be optimal for the text caption to image model. And then as the resolution gets larger, they found that decreasing that augmentation level worked better, I think. Maybe because beyond that first super resolution, then there were less artifacts in the image. Okay, so then evaluating it, they are comparing two images or two sets of images from two different models. One is Imogen and the other one is a ground truth, or one is Imogen and one is a model like DALL-E 2, and they're asking human responders to state a preference, yes, indifferent, or no. And then the results are that versus a lot of these competing models, then Imogen is more preferable in terms of alignment and sample quality. And so there's this idea in the results section of trading off between alignment, which is clip score, and sample quality, which is FID, and looking, controlling for the size of the language model and increasing the size of the language model for a given sample quality, increase the clip score higher than increasing the diffusion model going from text to image, because there's a very little difference in alignment from increasing the unit size of the diffusion model going from text caption to 64 by 64 image when compared to increasing the size of the large language model. And so the interpretation of that, I'm not sure, but it's more important to understand the text than pushing the quality of the diffusion model jointly trained with the text to produce this text described images. And finally, the thing we talked about at the start, which was this numerical stability trick, dynamic thresholding only improves the sample quality and image alignment across different levels of this weight. So the way these Pareto curves were produced is increasing the weight in the classifier-free guidance. And so as you increase the weight of the classifier-free guidance, then the samples are produced with higher probability of aligning with the text caption. But it's a trade-off, you see. So it's trading off the sample quality, which goes down because a higher FID score means lower sample quality. So I think that's about it for this paper. And we can leave the last 5 minutes for discussion.
I think it would be interesting for them to try another language model, because T5 is pretty old now. I was actually kind of surprised that they used it. Maybe, like, why didn't they even just use Bard? But maybe, yeah, I don't know. I wonder what how that would impact things, like whether we would see another huge increase in performance by just using a more modern language model.
Yeah.
I think it's because they need an encoder-decoder model. Because
That's fair.
right? Because with like the Bard is decoder, is it? The GPTs,
I think
GPT
all language model, like modern language models, or the state-of-the-art ones, are decoder only architectures.
Yeah, but with T5, do they need the encoder also? They do, right?
Yeah, it's got an encoder as well.
Yeah, I think that's why. Although there should be newer encoder-decoder models, maybe not. Oh.
Another interesting point is that it seemed to be more important from their study over the architecture to increase the number of parameters in the text to low resolution image model. So more parameters in the text to low res image model than parameters in the super resolution model. Because getting that first low resolution image that aligns with the text is important, and then upscaling that image whilst reducing artifacts seems like an easier problem. What's the most recent large language model that uses like an encoder decoder?
I don't even know. Maybe T5.
Yeah, I only know T5 also. Maybe new versions from T5.
What has that been replaced by? So what's the encoder decoder being replaced by?
Decoder only.
Okay.
So you don't have any. You don't have any. Actually, it might be encoder only, but I think it's decoder only.
And then encoder only, like BERT and stuff, they are still in use, right? Because they just that's how you create embeddings.
So is it just going from word embeddings and positional embeddings to decoding?
Yeah, it's just processing the text. Makes sense though, because usually when you're doing text processing or text generation, it's not actually it can be posed as a sequence to sequence problem, but it's actually just like a single sequence. It's not. I think it makes more sense, although they're even training it for translation. Like it makes more sense when you're doing like one language to another or like one modality to another. Maybe yeah. I'm trying to see if I can find out what Bard's architecture is, which is Google's newest language model, because T5 came out of Google as well.
I'm looking at this tree of LLMs. That's how I'm navigating which is which, and how Bard is a decoder only. You know this? Just search for LLM tree, evolutionary tree.
Could you post that link if there's a link?
Yeah, that's the first result. Just search for it. It's quite common. Yeah, that's the one. So you can see which is which, right? And the green one is T5s usually, I think. Because those are encoder decoders. They do both.
Okay. So then Flan UL2 seems the most recent iteration.
I don't know about this, but there is a T5 right before it, which should be good enough.
Cool. I think we'll. If anyone does anyone have any final questions, or should we end here? Nice. Let me stop there. Ben, thank you for